Hello and welcome. We will talk about NASA said no to Jeff Bezos' cheaper SLS mega rocket. Last year NASA doubled down on SLS right before Halloween. The end of October is the season for trick or treating the USA. Companies like Blue Origin and SpaceX are working steadily to lower the cost to get into space. For those that don't know, Jeff Bezos founded and funded Blue Origin since 2000. Blue Origin knocked on NASA's door with a proposal to reduce the cost of the Space Launch System (SLS). But the trick was on Blue Origin. When Blue Origin offered a commercial option to save money on the SLS, the company walked away without any treats. NASA slammed the door on Blue Origin's proposal, citing increased risk and schedule driven by additional testing and extensive modifications needed to adapt the current plans for SLS support equipment. To Blue Origin's credit, NASA seriously considered the offer before saying no. How did we get here? After the Space Shuttle program was determined to be completing the primary mission of building the International Space Station, the United States was left with a question. What was next? NASA's human space flight program had been stuck in low Earth orbit since the Apollo program. Growing attention to doing something that had not been done before started to surface. Enter the SLS, the next really big thing for NASA. Originally conceived from the Constellation program, SLS was to propel NASA into deep space. No rocket had been built that was that big and powerful. Nothing was even close except the Saturn V rocket, which had not flown since the 1970s. But SLS progressed slowly. SLS is currently behind schedule and over budget and could be over by billions of dollars once complete. The concept of SLS was simple: repurpose proven technology to reduce the development cycle. The design of the SLS was taking the solid rocket boosters from the shuttle and stretching them. Take the Space Shuttle main fuel tank and stretch it. Take the Space Shuttle main engines and stick them on the bottom of the tank. Design an upper stage that will leverage existing technology without requiring a lot of redesign. The problem? What seemed simple on paper ended up being a lot more complex. Apparently, stretching the design and making things bigger was a lot harder, more time-consuming and as a result costly than originally conceived. The lesson: anytime a major change, size, mission parameters, configuration, etc., is to be undertaken in rocketry, it requires a lot of effort. Detailed example of some of the proven technology on SLS, RL-10, credit Aerojet Rocketdyne. SLS is slated to use various legacy technologies. One such as Aerojet Rocketdyne's RL-10 series engine, which has a long legacy in spaceflight. It has played a role in placing hundreds of military, government and commercial satellites into Earth's orbit. Some notable spacecraft the RL-10 has helped heave into outer space, including Voyager 1 and Voyager 2, the first two spacecraft to reach interstellar space. Spacecraft that have gone beyond the confines of our solar system. This gives the RL-10 series engine more than 50 years of track record. It has been utilized as an upper stage of the United Launch Alliance's Atlas V and Delta IV launch vehicles. Newer iterations of the RL-10 have been slated to be utilized in the upper stage for the Omega rocket being developed by Northrop Grumman and the Vulcan rocket being developed by United Launch Alliance. Although the RL-10 has 50 years of data, the RL-10 that will be utilized on SLS will be modernized. According to the Aerojet Rocketdyne website, qualification efforts are underway for a modern version of the engine known as the RL-10CX. This updated engine design will include major components built using 3D printing technology rather than more traditional machining techniques that have been utilized for the prior 50 years. Aerojet Rocketdyne is betting that by incorporating 3D printing into the manufacturing process, the result will be reduced lead times and cost without sacrificing the outstanding performance and reliability demonstrated over the past 50 years of flight experience. Enter the next change for SLS. Initially, SLS will as planned to utilize the ICPS or the Interim Cryogenic Propulsion Stage. The 16.6 by 45-foot high ICPS would be powered by a single RL-10 engine produced by Aerojet Rocketdyne with the capability of producing 25,000 pounds of thrust and weighing 71,605 pounds. Fully fueled, 7,690 pounds. Dry weight. To get to the ultimate goal of NASA, SLS will need a more powerful upper stage. Enter the EUS or Exploration Upper Stage of the SLS. The EUS will feature 4 RL-10 engines increasing the thrust capability of the upper stage to 97,000 pounds. That is a roughly 4x increase. The upper stage will increase in volume to have a width of 27.5 and a height of 57.6 feet to accommodate additional propellant and oxidizer. The fully fueled weight of the EUS would be roughly 250,000 pounds. 28,940 pounds. Dry weight. So, what was wrong with this approach? The ICPS and EUS are radically different and will require major design changes to get to the final design. As we discussed before, the cost of the new design for the upper stage is not cheap. It is designing a whole new stage. Under growing pressure, NASA looked to outside companies for suggestions on how to maintain budget and schedule without compromising on the mission. Enter Blue Origin with an innovative concept on how to help reduce costs. When NASA put out a request back in 2017 to see if there were alternatives that could be considered, people hoped that companies like Blue Origin and SpaceX would answer that call. Blue Origin answered with a concept so simple it was radical. Use technology developed by Blue Origin and apply it to SLS. The plan to use the already developed Blue Origin technology could save a lot of money for NASA and US taxpayers. This would especially be good if Blue Origin had already started to develop its large upper stage, which they have for the New Glenn launch vehicle. With the ICPS already in process for initial flights, NASA recently evaluated the alternative proposal for the SLS upper stage that is needed for future planned missions. On October 30th, just in time for Halloween, the NASA Marshall Space Flight Center (MSFC) gave their answer officially with a justification for other than full and open competition (JOFOC). For those that need a brief understanding of U.S. government procurement, U.S. Federal Acquisition Regulations or FAR, it is generally accepted to have a competitive environment when bidding for government contracts. The JOFOC is a process required by the U.S. FAR awarding contracts that are not competitive. NASA cited several reasons why the original plan to leverage Boeing for the EUS rather than alternative proposals. NASA rejected Blue Origin's bid to save U.S. taxpayers money and time in exchange for SLS to maintain performance and avoid potential delays associated with bringing in a new variable at this stage of the game. So SLS will stay the same. What did Blue Origin offer? According to the NASA document, Blue Origin offered a commercial solution for an upper stage that utilized 2 BE-3U engines. Which sounds like a New Glenn upper stage or close to it. These BE-3U engines are, according to the Blue Origin website, variants from the already flight-proven BE-3PM engines. On the 23rd of November 2015, BE-3PM thrust the New Shepard above the Kármán line. Not only did the BE-3PM lift the New Shepard into space, the engine then reignited, allowing for a historic soft landing, marking the first flight to space and back for a propulsive launched and landed vehicle. Yes, Blue Origin did that before SpaceX did. This was a great feat, but to top that, Blue Origin then utilized that same engine to successfully repeat the feat 4 more times. Although the BE-3U doesn't have 50 years of flight heritage like the RL-10, it is based on a proven concept. The BE-3PM can generate 490 kilonewtons, 110,000 lbf thrust at sea level. This translates into over 1 million horsepower if you wanted to count. More capable than many engines, the BE-3PM has the capability to throttles down to 90 kilonewtons, 20,000 lbf. This throttling when returning to Earth provides Blue Origin the ability to provide a gentle vertical landing on the pad. VE-3PM utilizes high-performing liquid oxygen and liquid hydrogen similar to that of the Space Shuttle main engines, SSME. As an additional perk, Blue Origin designed the VE-3PM for operational reusability with minimal maintenance between flights, according to the Blue Origin website. What was offered on the Blue Origin proposal to NASA for an alternate SLS upper stage was two VE-3U upper stage variants. According to the Blue Origin website, the VE-3U, 3U standing for the upper stage, is optimized to operate in the vacuum of space. It will feature back-to-back turbine assembly and a larger nozzle. These optimizations allow the VE-3U to generate 710 kilonewtons, 160,000 lbf thrust in a vacuum. The extended nozzle to compensate for the additional pressure difference grows the height of the engine. Larger, optimized bell nozzle configurations are common for upper stages when attempting to maximize the efficiency of the rocket. The SLS-EUS is utilizing 4 RL-10 engines. It produces upwards of 97,000 pounds of thrust. In comparison, if two VE-3U engines were utilized, the upper stage would be capable of producing upwards of 320,000 pounds of thrust. That increased thrust is much more than NASA requested. The VE-3U was also capable of restarts, which allows for in-orbit operations. Some rocket engines can only be ignited one time. Multiple ignitions require different technology. It seems like a slam dunk, right? The more powerful, potentially less expensive second stage from a company that innovated new rocket engines and designs. So, did NASA look at this proposal? Yes, but the catch: NASA received 2 responses for the production and evolution of the SLS. NASA received one alternate response for the EUS stage, which was received from Blue Origin. NASA deemed the alternate response received as an approach that appeared to recommend the use of a commercial item as an alternate solution for the custom-designed Precision Launch Vehicle's second stage. NASA previously stated it does not intend to acquire a commercial item. Nonetheless, when Blue Origin proposed a commercial solution as an alternate, NASA, to their credit, analyzed whether the commercial item could indeed meet the government's requirements. NASA reviewed the Blue Origin proposal in spring 2019 as part of an SLS trade examining potential upper stage engine configurations that were thought to feasible to meet the 2024 threshold for the first launch. Trades are done to examine technical, schedule, risk and cost factors when attempting to determine the best options for design. NASA determined that the Blue Origin commercial proposal did not meet the requirements as proposed, and further that the commercial item cannot be modified to meet the requirements, and finally that the system requirements cannot be changed to accommodate the commercial item. 3 specific items were called out: the NASA response, 10 Mount co-manifested performance requirement. Total SLS stack height less than 390 feet to fit vertical assembly building, VAB, door end of life acceleration limits on Orion service module. It seems that the biggest challenge for the utilization of the Blue Origin alternate upper stage was the physical dimensions. The proposed NASA EUS to be built by Boeing has an overall height of 57.6 feet. The Blue Origin New Glenn upper stage is taller, coming in at roughly 76.9 feet based on the 2018 New Glenn user guide. Although there are some differences from the published 2018 user guide to the current information on the Blue Origin website, this should be a good representation for what NASA was referring to when NASA outlined that changes to diameter or height will immediately impact the 390-foot maximum. Since using a Blue Origin New Glenn style upper stage for SLS would have increased the height by almost 20 feet, the SLS was proposed at 365 feet. Adding another 20 feet to it would increase the total height to nearly the 390 caps without accounting for any additional adapter stage. Having to also deal with the diameter difference, it is very possible that the proposed upper stage would have been at the 390 feet maximum height or beyond if it needed to be stretched to add additional fuel or adjust for universal stage adapter interstage changes. As a side note, each door in the VAB is 456 foot tall, so with some adjustment to the requirements, these and the other objections could have been accommodated. credit NASA ML2OR Mobile Launcher 2. The larger reason why the Blue Origin proposal was likely passed on was the impact on all of the other systems and contracts associated with a change to SLS. For example, the ML2 Mobile Launcher 2 procurement and build were already released with the understanding of the SLS configuration. The ML2 is an example of the massive investment that NASA and Boeing have already made. NASA's current stages contract with the Boeing Corporation NNM07AB03C requires the design, development, test, and evaluation (DDT&E), production and operation of the stages launch system through Artemis 1 and 2. The stages contract is a hybrid contract that includes cost plus award fee (CPAF), cost plus incentive fee (CPIF), firm fixed price (FFP), cost contract line items. Under the stages DDT&E contract, the development of a highly specialized workforce, infrastructure, and special tooling to produce materials and components for the core state and EUS. Making a change to the SLS upper stage would have an impact on the Boeing established workforce that is trained and certified to perform stages' unique processes and operate stages' unique infrastructure and tooling. NASA highlighted that to leverage manufacturing and production efficiencies for SLS, the EUS design incorporates significant commonalities with CS. The diameter of both the CS and EUS is 8.4 meters and as a result will utilize the same tooling and infrastructure already developed and in places such as equipment to assemble the domes, barrels and large cryogenic LH2 and LOX tanks. By removing a portion of the work that has been planned for Boeing, the costs of the SLS core stage would need to absorb the reduced manufacturing efficacy, resulting in cost increases. In addition to the three highlighted technical challenges, and the loss of manufacturing efficiency that Boeing would need to pass along, there would be increased complexity for manufacturing the rocket. The Blue Origin design would need to be integrated into the NASA-Boeing SLS design. Cross-communication between various contractors is possible but adds additional work. So, in summary, the time has come and passed for other bidders to make a mid-course correction on SLS. Right, wrong or indifferent, SLS design is conceptually set. To make major changes at this juncture would send massive ripples through the entire supply chain of SLS. The justification for other than full and open competition (JOFOC) set the direction for Boeing to build a powerful, expensive, low-rate initial production LRIP rocket for NASA to over the coming years. Thank you for watching. Please subscribe my channel, like video, and comment. Goodbye until new video.